Our next step in our talk about, so far just a little recap. We had regular languages. Those were languages where you have a finite state machine, but you don't need any memory. Then we found out there was a bigger class called context-free languages, which were, there was a finite state machine, plus you had this very limited piece of storage, a stack. It can only build as high as, at each letter you read on the input. At worst case scenarios, you add 1 to it, so it can only get as big as the input. It could never get bigger than that. And if you're popping along the way, it'll even decrease in size. Then we had another example, another class, which was context-sensitive languages. And there you basically have a state machine, but you get to use more, you have more freedom with your memory. You have a finite amount of memory. And every time you read an input, a letter from the input, you can run up and down your memory and make changes to the fields in it. So you have a lot more freedom. So the question is, so basically context-sensitive, all three of these, context-sensitive, context-free, and regular, were languages where we would have an input, you know, let's say like A, B, A, something like that. We would read each of the inputs, we would read an input, and what would we do? Maybe we move from state to state, and maybe we adjust our memory, make changes to our memory. Then we go, then after that computation is done, we come back and say, move to the next letter. And then we bounce around from state to state, maybe we read and write from memory, go to the next one. Eventually we hit the end, and we're always in a state of either yes or no. The regular languages, some of the states were marked yes, some were marked no. Context-free, in order to answer yes, we had to be in the yes state, plus we could make rules about the stack. The stack has to be empty, or the stack has to be not empty, or something like that. And the context-sensitive languages, we have to get to some yes state, plus some description about our memory has to be true. But we always get to the end. We always get to the end, and we eventually answer yes or no. So the question comes up, is it possible to have a computation where as you're reading the input, you know how we read the next letter, then we perform a computation, then when the computation's done, we come back, we get the next letter. What if we went into the computation and it just went on forever? It never came back asking for the next letter, so we could never get to the end and answer yes or no. So the question is this even possible? And there were some famous people in the world of computer science, and they were all here in New Jersey. There was a guy named Church, Alonzo Church. I don't know if you've heard that name in any of your classes. And then he was a professor at Princeton University, and he had a bunch of, like, probably about 10 or 11 famous students of his who got their PhD with him as an advisor. And a very famous one is Alan Turing. Does that name come up in any of your classes? No? Okay, but he's very, very famous. Like the biggest award in the world of computer science is called the Turing Award. And so that's kind of like the Academy Awards for computer science. So, and he was British, and during World War II he was breaking codes and stuff like that, and then he came here, got his PhD working with Church, and became a very famous computer science person. Another one was a guy named Martin Davis, who is a professor at NYU. He was actually my professor at NYU, so got my NYU shirt. So I learned the theory of computation from Davis. So the question that came up, and it was kind of these two guys, but this guy got mostly the credit for it, is this thing called the halting problem, which is an example of a language where as you're going through the inputs, you might hit an input and get stuck forever. And actually the guy Davis was the one who gave it the name, the halting problem. So he gets credit for giving the name, but Alan Turing gets credit for proposing the problem. And so it goes like this. This is the concept of a Hall-Payne problem. Suppose we had a program, and I'll use, like, maybe I'll use my name and one of your names just as an example to show that this is a random problem. So let's say we'll use the name Bill. So we have a program Bill which takes in a string S, and it'll go like this. So I'll make it look like C++ or Java or whatever. I'm going to say if the first letter of the input equals an A, or, is that or in your favorite language? Okay. Or is it different than our, okay. Or the first letter is a B, then what we're going to do is, just for fun, we're going to go into an infinite loop. While 1 is equal to 1, which will be true forever, we'll do nothing. And then we'll finish here, and we'll finish here. Okay. So this is a program that, depending on what the input is, it may go into an infinite loop, or it may not. Now you're probably thinking, why would somebody do this? We're just doing it to make a demonstration. So for example, if I took this program Bill, and I said Bill with the input of A, B, C, what would happen? Would this go into an infinite loop, or would it stop? Okay, it'll go into an infinite loop because the first letter of the input is one of these two. Okay, so this would go into an infinite loop. I don't know if you've ever been to California where Apple Computers is, but they have their complex has a big road that goes all the way around the outside, and it's called Infinite Loop. It's the name of the road. They got the town to approve that being its name. Okay, what if we had Bill of X, Y, Z? Would that go into an infinite loop, or would that stop? That'll stop because the X is not one of these. So X, Y, Z comes into S, we look at the first letter, it's not A, it's not B, so we skip over this, and there's nothing else to do. And if you think about it, this could be kind of considered a state in your finite state machine. If we see an A or a B, we go to this state. And if we don't see an A or B, we go to this state. So if you think about it, all programs are states where you're reading and writing from memory. And what if we had a variable? If we said Bill of X, but X is a variable and has some content in it, would it loop forever or would it not loop forever? Well, you'd ask, what is X? Right? Let's say if X was B I L L, and that was a variable, then it would be the first letter of this. So this would go into an infinite loop, right? So this could be a variable, or you could actually put the string in. Okay. So here's an interesting question. Suppose somebody came along and said, so now we can formulate the question. Suppose somebody came along and said, wouldn't it be nice to have a function called does it halt? And it would take as input a program plus, I'm going to do a semicolon, plus an input for that program. So for example, the program would be this whole thing, and then maybe an input. The input is like X, Y, Z. So the input to the program, the input to this program, does it halt? And this is going to answer yes or no. Does it halt? It's not going to actually run the program. It's just going to give an answer yes or no. Will this program being fed this input, will it halt or not? Like what we were just doing. We were just answering yes or no. So this could be considered a language, because of all the possible programs and corresponding inputs, we'd have to answer yes or no. So what if we wanted to build a finite state machine using some memory that could answer this question? Could we write a program called Does It Hold? So what do you think? If we did, it would be a big program, right? We'd be almost compiling this thing and then depending on the input to see whether it would go into an infinite loop. And that would be a pretty complicated program to write. Okay. But we have to just, we want to make sure we understand what it's doing. It's taking as input a program, and then it's asking, does it halt or not? Okay. So, suppose somebody comes along, suppose like these great computer scientists from Princeton or whatever the great school is these days. Suppose they come along and they say, yes, we did it. We spent all night, or, we spent months, and we created a program called Does It Hold? And it takes in a program, then we kind of need a little divider, maybe a semicolon, and then an input, and it answers yes or no. Yes or no. Whether this program will halt on this input. Well, if we were to describe this as a language, how would we describe it? The language of, I'll put D-I-H, the Does It Halt language. What would be the description of this language? It's all P's and I's such that, P of I halts. Right, this is the language of all P's and I's such that if I was fed into P, the program would halt. Okay. Now, okay, so these famous people come along and they say to us, we did it. We wrote this. We wrote this routine, this big program called Does It Halt? And it takes as input a P and an I, and it always answers yes or no. So what if we decided that we wanted to say, does it halt, and feed as input a program followed by itself? Now, the example I had before, I kind of wish I left it up. The example I had before, right? Remember I had Bill takes in a string, S, and blah, blah, blah. I could give anything as S, X, Y, Z, A, B, C. What I could also do is I could take the program Bill and feed that in as its own input, and the first letter would be B. So I forget what it said, it would go into an infinite loop, right? So you could feed into a program itself, especially if it's looking for strings, because a program is a bunch of strings. There's also a very famous mathematician named Gödel, G-O-D-E-L, who made an elaborate proof that all programs can be converted into a unique number by multiplying prime numbers together or something like that. But we don't have to worry about that here, because this will work fine. If somebody claims they've written, what our goal here is to show that this thing could never be done. That's our goal here. But suppose somebody claimed they did it. They created this program. If we decided to use it, but always feed any program P, we always feed as input the program itself, which again, this would be odd. What language would this be? This would be the, I'll call it the XX language. What would this language be? This would be all the words X such that if you fed X to itself as input, halts. Right? It's just an odd thing to think about. So this is what these people touring in church, this is what they were thinking about in the 1930s or 40s, right here in New Jersey. So this is the language of all programs that if you fed it itself as input, it would halt. Okay. Now suppose someone in this room comes along and says, I got my own program. So I'll use one of your names. Oh, okay. Okay. So let's say the Deep program. And I'm just using a name here to show that anybody can do this. You take in a string S, and what you do is you say if does, so you call up these people and you say, can I have your routine, I want to use it as a subroutine, can I have your program? And they send you an email and they copy it over to you. So you say, does it halt? If does it halt on S, no, does it halt means two things. If does it halt on S, semicolon S, if that halts, then what you do, if it halts, you go into an infinite loop. While 1 equals 1, loop forever. And same thing as before. So this is your program. So yeah, let me just recap this. If somebody comes along and says, I have created a program that if you give it as input a different program plus a random input, I can always answer yes or no if it will stop or loop forever, if it will halt or loop forever. They could always answer yes or no. Then we made an observation, well, if we take the language of does it halt out of all programs where you feed itself in as input, that's the language of all programs that having itself as input would halt. Okay, that's just an observation. This is like a lemma, just a side fact. Then you come along and you say, I'm going to write this program. So what does your program do? You take in some string, you feed it to does it halt, you feed it to this thing, and you feed its input to itself. And if this thing answers, does it halt? If it answers yes, your program goes into an infinite loop. And if it answers no, your program stops. Okay? So again, this looks like a complete waste of time. But, so now, here's the interesting thing. How would you describe this language? I'm going to call this the deep language. It's all x's. Maybe I should have made that x deep. Okay, all x's such that what? You know what? Let me change these to x's just to be consistent. This will matter in a little while. So a string x, and you feed x to itself. Okay, so the language that is produced by the deep function is what? It's all x's such that if you fed x to itself, what would happen? Well, no. If you feed x to itself, if this answers yes, if does it halt answers yes, equals yes. If the input program fed to itself halts, your program goes into an infinite loop. If the program fed to itself doesn't halt, meaning it goes into an infinite loop, then you stop. So you're the exact opposite of this language. Does that make sense? Okay, so it would be all x's such that if you fed x to itself would not halt. So now we have the situation where, so let me just do one more recap. Someone claims they wrote a program that if you fed as input a program and some random input, it could always answer yes or no. Yes or no, whether it halts or not. That's why it's called the halting problem. It answers yes or no. Will this input fed into that program halt, yes or no? We make an observation that if we use that does it halt and feed all programs into themselves, we can create a language of all x's such that if you fed x to itself, it would halt. Then you come along and you write this program, which is the exact opposite. You say, feed x to itself. If x fed to itself halts, then my program goes into an infinite loop. You did it intentionally. And if it answers no, that it goes into an infinite loop, then your program stops. So your language is the exact opposite of this, of what we say in set theory, the complement. So the language XX is equal to the complement of your language. Everything in here that's a yes is a no here, and everything that's a yes here is a no here. They're the exact opposites of each other, right? And we've seen that before. Like if we had a regular language that said, you know, you have to read a bunch of A's first and a bunch of B's second. Well, anything that would answer a no is in the complement of the language. Anything that would answer yes would not be in the complement of the language. So we've put this together. Now, here's the interesting question. What would the answer be? What does deep D that's your program. It has one input. What if we fed it, we take all of these characters and we fed it into itself? So we fed deep D into deep D. Would this halt or not halt?
Not halt. It does not halt.
What's that?
It does not halt.
It doesn't halt or it does halt? Well, let's see. If we take deep D, take all this code, feed it in here, does it halt? So we asked this routine, if I take deep D and feed in deep D, does it halt? Now, if this answers yes, then deep D with deep D as input would go into an infinite loop. If it answers no, meaning deep D fed into deep D goes into an infinite loop, then your deep D fed into deep D would halt. Right? So it doesn't make sense, right? It would be like saying if x equals 1, then x equals 9. But no, we're making a statement that doesn't make sense. So we'd have to look at this code and say something here is obviously can't exist. Well, you know, strings exist and if statements, I've been using those my whole life, open, print, close, print, that's all fine. The thing that can't be true is this. There is no way this thing could be answering yes or no. Because I've shown a way that if it gave me a yes, I would prove the answer is then no. If this thing tells me deep D passed in as input to deep D halts, deep D passed into deep D then won't halt. So there's a contradiction here. So the conclusion is, this is what, you know, one of the things that made Turing famous is the halting problem. Can you code this thing? Can someone code this? The answer is no, it could never be coded. So now we're looking for an explanation for why it would never be coded. And but that, I mean, that's a very important result, is that this thing could never be coded. So what's going on here is if we were to if we were to code this, what would the answer? So we would have a state machine, right? We've done this before. You know, states bouncing around to each other, and we'd have some memory. We'd have some memory cells, and then we'd also have, so the state machine can read and write to the memory, and we would also have, we would also be reading the input. So let's say the input was, deep D. Open paren, string, you know, I wrote out the whole program, and then I put a semicolon, and then I gave an input like DB, you know, blah, 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 wrote out the whole program again. So this is our input. So we would read D, and we'd do something. We'd read an E, we'd do something. We'd read another E, we'd do something. But if we eventually got to the end, we would be in either a yes or no state. So if we've proven that this cannot be computed, somewhere along the way, we hit an input and just got stuck. We went into an infinite loop. And we couldn't finish the computation. If we make it to the end, if we make it out to the last letter, and we're in a yes state or a no state, that's it, we're done. We answer yes or no. So what Turing proved is that there are some problems that you never make it to the end of the input. So we want to go back to our hierarchy. We have regular languages, context-free languages, context-sensitive languages, and now apparently there's something else out there. The ones that are like the Halting, so for example, the halting problem. The halting problem is here, right? And we can have examples of ones that are in different states. So we kind of need a name for this one now. Okay, so can you think of a name for this layer? So this is now turning into a hierarchy, right? Things that are subsets of other things. And in a class or two, we're going to call this the Chomsky's hierarchy. Chomsky is a famous language professor at MIT, like natural language, like English and Spanish. But parsing of languages and parsing of computer programs is the same thing, so it's really not a lot of difference. So now we need a name for problems like the halting problem, where, well, first let's look at some properties of these. So if you gave, so let's, instead of calling it does it halt, most textbooks will just call it halt, but that means you're asking the question, the yes or no question, does it halt? So suppose we have halt of P and I. You give a program, you give an I, and apparently what Turing proved is you could never write this thing so that it will always answer yes or no, no matter what you give as input. He proved there are going to be times when you're going to get stuck and never finish the computation. What if the answer was yes? Can you think of a way to write a program that if the input was a yes, yes it does hold, you could then answer yes. If it was no, your program may go off into an infinite loop, but if it's yes, if it's a member of the set, it will answer yes. Is there a way you could think of doing that? So for example, you're given two inputs. You're given a program and an I, and you're trying to find out, if I feed I into the program, will it halt or not? And Turing proved that sometimes you may never arrive at the answer. You may be computing forever. But if the answer is yes, it does halt, is there a way? So yeah, let me try. I know it's a little confusing. Let's say I had a P1, I1, P2, I1, P1, I2, P2, I2. And some of these answer yes, and some answer no. Right? Different combinations of input answer yes or no. What Turing proved is the ones where the answer is no, instead of you reaching the end of the computation and saying the answer is no, you might go into an infinite loop and never finish the computation. But the ones where the answer is yes, is there a way to figure out what those are? Like if I only promise to give you good inputs, this one or this one, is there any way that you could write a program that will say, all right, well, that one's a yes, and that one's a yes, but if you give me this one, I'm gonna be in trouble. I'm gonna be computing forever. So is there a way, instead of answering either yes or no in every case, at least I can answer a yes if it's a yes, and just don't ask me the ones where there's a no. So is there a way to do that? In other words, I want to design a machine that if the program and the input does halt, I can then answer, yes, that does halt. If it doesn't halt, then you allow me to go into an infinite loop and you don't get mad at me. So is there a way to do that? So we're going to write a program, halt, give me P and an I, and I'm going to do this. I'm going to, let's say, compile P, and then I'm basically going to run P, feed it I. That's step one. Step one, I'm going to run the program P with the input I. And then step two, I'm going to print the yes. Now, under what scenario would this program print a yes? If I ran the program P with I as input, and it actually finished, then the next thing I'll do is say yes. If I run P on I and it goes into an infinite loop, this yes is never coming out. So this is a program that if you gave me a P and an I where the answer is yes, this program will always tell you yes, it's true. But if you gave me one where the P and the I does not halt, this would actually go into an infinite loop and I'll never give an answer. So you might think, why not give a P and an I, let it run for like a long amount of time, and if it doesn't answer, we'll just declare, oh, that's an infinite loop, right? Are you thinking that? Like let it run for 3 hours, and if it doesn't finish after 3 hours, well, then it's in an infinite loop. But you might think, well, maybe in 4 hours it'll finish. So there is no time period for us to say, this is definitely in an infinite loop. So it would just have to run indefinitely. But one thing that's true about the halting problem is if you gave it a P and an I as input, and this is really one big long input, right? It's the program, semicolon, and then the input. So it's just one long input. It's not 2 inputs. If you gave it one where the answer is yes, we could answer yes. But if you gave it one where the answer is no, we'll go into an infinite loop. Okay. So these are the kinds of problems we could either, I should have wrote this in a different color. Let me write this outer band in a different color. So everything that's in blue, we could always, anything that's in blue, we can answer yes. Yes, when the answer is yes. Everything that's in red, we can answer yes or no. If the answer is yes, we answer yes. If the answer is no, we answer no. The stuff that's out here, we can answer yes if the answer is yes. But if the answer is no, Turing proves we'll go into an infinite loop, searching for the yes. So we have to come up with a name for these. So if you had to make up a name, what would you call these? Yes only, something like it. Yes only languages. Yes or infinite loop. It's the class of languages where if you give me an input that's in the language, I can answer yes, and if it's not in the language, I go into an infinite loop. Everything that is in red, if you give me an input, I will always answer yes or no. When I get to the end, I'll give you a yes or no for sure. This new class, I've showed here, if the answer is yes, because we're talking about halting versus not halting. This would run to a point, and then after 2-3 hours, or however long it takes, it would stop, and I'd get to this line, and it'd spit out yes. But if this goes into an infinite loop, I'll never spit out anything. So these are the class of problems. The halting problem is an example of a problem where it will answer yes if the answer is yes, but go into an infinite loop if the answer is no. So one name for this could be yes or infinite loop, yes only. So we need to come up with a name for this class. Yes only? Is that a good name for the class? Well, that would mean, no no's. Okay. So, you gotta think of a name for this class. And then this will come up when we go over proofs in a later class. So, we're at the point where we need a name for this class. So, I want to go back to an example. Let's look at a language. What was it? A to the I, B to the I, where I is greater than 0. So do you remember where this language fits into this picture? This is the one where the number of A's and the number of B's have to equal each other.
It's context-free language.
That's context-free and not regular, right? So that would be around here. This language requires us to use a stack.
Yeah.
Okay, now, we could do this. We could write a program that will print out every word in this language. So it would go like this. Let's call it the AB language. And it takes as input a string, S, and it, I'll take in a blank string. I'll say S equals an A. Is that what you use for concatenating strings in your favorite language? Okay. A concatenated with S, concatenated with a B. Okay? So all I'm doing is saying whatever the input is, I'm going to put an A in front of it and a B after it. And then I'm going to print it out. I'm going to print out S. And then I'm going to recursively call this function again. I'm going to say A, B of S. So you've seen recursive functions, right, where a function calls itself? Okay, and it's a tailed recursion. It's always better to have the recursion call be at the very bottom. It's a programming languages concept. Okay, so what would, if I ran this program, if I said AB with nothing as input, just blank as input, what would this program print out? It would start off with a blank, so S is blank. I put an A in front of it and a B after it, so it's basically AB. I print AB, so it would print the output would be, it would print AB. And then it would call this function, the AB function, passing in AB. So pass in AB, and what would this do? This would put an A before it and a B after it, and what would the next thing it print out? It would print out A, B, B. Now S is equal to A, B, B, and now I call AB with, so it comes back in, it puts an A on the beginning, a B on the end, and it prints out A, B, B, B. How long will this program run? This will run forever. Nothing's stopping it, right? What it's going to do is it's going to print out the entire language. So this is all the words that have an A. A's before B's, and the number of A's and number of B's match. This program will print out the entire language. So it's a recursive program, and it's printing out every word. So we call this language a recursively enumerable language, which basically means, let me use a different color for marker. This is a recursively enumerable a recursively enumerable language, meaning I can write a recursive program, and it's usually good if you can start it with a blank, and then just have it recursively spit out the whole language. Print out everything that's in the language. That's called a recursively enumerable language. Okay. So, this doesn't mean if something is not in the language, I can print it out. But maybe I can. And everything that's in the complement of the language. But if I can write a program that can recursively print out everything that is a yes, right? So these would all be yeses for this language. These would all be yeses. If I can write a program that can print out all the yeses, then that language is called recursively enumerable. I can print out all the yeses. Even if I can't print out the no's, if I can print out the yeses, they're called recursively enumerable. And then if I wanted to, if I can recursively enumerate the language, I could, if you gave me an input string, I could recursively print out all the languages and see if what you gave me matches. Right? That's one way I can check if your input string is a member of this language. I can recursively enumerate the language and each time check, does it match, does it match, does it match. Now, if you gave me as input, if you gave me as a test input, A, B, B, this should be a no. We should answer a no. If I recursively enumerated the language and said, does this match this? No. Okay. Does this match this? No. Does this match this? No. And I kept going, I'd be going forever. And I'd never answer yes or no to you. So any language that is recursively enumerable is a language where if the input is a yes, I'll eventually find it, right? So they decided to call this language, this yes-only language, they decided to call it the language, the set of all recursively enumerable languages. Recursively enumerable language. And of course, that's long, we'll use the abbreviation RE. RE. Recursively enumerable languages. And if, just as a side fact, and we could go, what I'll do, probably won't take up the whole course, but, oh no, maybe we'll take up the whole class. We could talk about this entire diagram, start to finish. And this is, again, like I said, this is called Chomsky's hierarchy of languages. And what we can do is we can go through examples where, like, show that a language is here but not here. So, for example, this language we did here. Do you remember how we proved? We can demonstrate it's here by creating a finite automaton with a stack and showing it could answer yes or no to everything. How did we prove it's not regular? We used the pumping lemma. The pumping lemma proved that we are required to use the stack. We couldn't do it without a stack. So that proved it was here and not here. And then we'll go over we'll go over this whole chart and just go like, here's a language that's here but not here, here but not here, here but not here. But one side effect, I'll just say as we're ending today, if you can compute, if you can recursively enumerate, and I'll show this in another class, if a language L is recursively enumerable, you can spit out everything that's a yes, and the language's complement is also recursively enumerable. let's just say that's true. In other words, can we recursively spit out everything that is not in here? So for example, A, B, well, A is not a member of this language. B is not a member of this language. A with one B is not a member of the language. A, B, B is not, like if we could write a routine that can spit out everything that is not in this language, that language, the complement, would also be recursively enumerable. So if a language is recursively enumerable, meaning we could always tell you all the ones that answer yes, and its complement, we could always tell you which are yes, then that means we can answer yes or no to both of them. So if these are both true, then these are, and this is a name, if this is true, if L is recursively enumerable and its complement could also could answer yes or no, that means we can answer yes or no. So then we would say L is recursive. Recursive, which I think is a little bit confusing, but here's kind of the explanation for why that name comes up. Suppose you had a language that was recursively enumerable and its complement was recursively enumerable. Could you build a machine that will always answer yes or no, no matter what you gave it? And the way we can do that is we'd have a program, let's call it recursive, that takes in an input, a string, S, and says, start running it on the machine that can enumerate L. So start enumerating L. Enumerate L. Well, I have to kind of spell this out, but basically what we'd be doing is we could enumerate L and look for a match to see if it matches S. Now the problem is if we never find it, we'll just keep searching forever. But we let the L language, let that run for 10 minutes, then let this one run for 10 minutes, start enumerating these, looking for a match. Then let this go for 10 minutes, then let this go for 10 minutes. Eventually, one of these two will answer yes. This will either answer yes or this one will answer no. But eventually we'll hit an answer. So I'll write up a more formal proof of that, but that's basically what the idea is. So basically, if we could write a recursive program that spits out every member of a set, and we could also write a recursive program that spits out every member that is not in the set, we could put these two together as subroutines and make a routine that will answer yes or no to that language. So another name for, context-sensitive languages are the languages that we always answer yes or no, no matter what you give it. So we could also call these recursive. Meaning we could always answer yes or no. The language we could always answer yes, and its complement we could always answer yes. Okay.